All right, here we go. Taylor Series Part 4. This is going to be hopefully a little bit shorter than the last one. We're going to take a look at a couple of different polynomials we haven't looked at yet, and then try a numerical approximation. So suppose I want a series for e to the x. Well, this is going to look funny, right? F of x equals e to the x. If I go through my process like I did before of, well, let's take the first derivative, and then let's take the second derivative, and then let's take 100,000 more derivatives, and look, we always get e to the x. What if I want to center this at a equals 0? So that means that f of 0 is going to be e to the 0, which is 1. F prime of 0 will be e to the 0, which is still 1. And f double prime of 0 will be e to the 0, which is still 1, which is going to make all of the coefficients in our series equal to 1. So if I throw this back into my formula, the f of a plus f prime of a, x minus a, f double prime, and so forth, all the a's are zeros. So what I end up with is this, a 1 plus 1 times x plus 1 times x squared over 2 factorial plus 1 times x to the third over 3 factorial, x to the fourth over 4 factorial, and so forth. This will keep going until I get to x to the n over n factorial, and because it's infinite, it'll keep going from there. Now, if you don't believe that's actually e to the x, just for fun, try deriving it. The derivative of 1 is 0. The derivative of x is 1. All right, so here I'm going to write it like this. The derivative of x is 0. The derivative of 1 is 0. The derivative of x is 1. This, when I derive it, the 2's will cancel. Here, when I derive it, that 3 that drops in front will knock out 1 3 on the bottom. Over here, the 4 that drops in front will knock out the 4 that's at the beginning of the factorial on the bottom. And I'll end up with just the 3 times 2 times 1 part. You realize that when I go to derive it, I get the same series as I had before, which shouldn't be surprising because the first derivative of e to the x is e to the x. So keep deriving it and deriving it and deriving it, and you'll still get the same exact Taylor series over and over and over. So, if you're home and you're bored and you want to try 10 derivatives of the series, I'll bet you get the same thing every time all over again. So now here's a question. Let's find the error in approximating e to the 0.2 for n equals 2, and then maybe we'll do a couple of more after that just to see if it gets any better. Now, for n equals 2, I'm going for 2 terms, so a second degree, right? So maybe I should specify for degree 2. So e to the 0.2 is going to be approximately 1 plus, I'll replace that first x with a 0.2, and then my next one will be 0.2 squared over 2. So that third one is the only one that I really need a calculator for, right? Take 0.2 and square it, and now divide that by 2, and you get 0.02. Now add 0.2 and add 1, and I get 1.22. Okay. Now, what is the actual value of e to the 0.2? So on my calculator, I do e to the 0.2. And I get 1.2214. All right, so 1.2214. Boy, that's pretty close. So the actual error is going to be 1.2214 minus 1.22. The actual error is 0.0014. If you want the relative error, then you've got to divide it by the actual value. So take that and divide it by 1.22, and you'll see just what a tiny error that is. All right, if you want to try it again for n equals 4, then go all the way out to 4 terms. So 1 plus x squared, x to the third, x to the fourth. So go all the way out here. It's going to take a little bit more computation. But what you'll realize is that for e to the 0.2, that Taylor polynomial is a real good approximation for e to the 0.2. Now, just like those linearizations that we did back in the days of Calc 1, these are good approximations very close to the center. So 0.2 is very close to the center of 0. If I start wandering too far away from there, if I try to use this polynomial to approximate e to the 0.7 or e to the first or e to the 1.5, I'm going to get lousy approximations, especially if this series happens to diverge a lot from the actual value. Does it not? We'll find out in the days to come. All right, back in the day, we had talked about integrating things like e to the x squared. Is it possible to build a Taylor polynomial for e to the x squared? Right? What does e to the x squared look like? Well, if e to the x is 1 plus x squared over 2 factorial plus x to the third over 3 factorial, then this would end up being what? This would end up being 1 plus, instead of x, we'll have an x squared, plus x squared squared over 2 factorial, plus x squared to the third over 3 factorial, plus x squared to the fourth over 4 factorial, and so forth. So if you want to clean that up a little bit, e to the x squared is 1 plus x squared plus x to the fourth over 2 plus x to the sixth over 3 factorial plus x to the eighth over 4 factorial, and so forth. Now, remember we said that there was no direct way to integrate an e to the x squared, that you would have to use some other method to integrate e to the x squared? Well, here is just such a possibility, right? If I want to integrate e to the x squared with respect to x, I can integrate both sides. Just like I mentioned before, we can derive both sides, and that's okay. Here we can integrate both sides, and that's okay. So the integral of e to the x squared is approximately x plus x to the third over 3 plus x to the fifth over 10 plus x to the seventh over 42, and keep going like that. And now, depending on how many terms, if you want to actually make this a definite integral, like if you want to find the area between 0 and 1, then you're going to have to stop at a certain number of terms in order to come up with an approximation so that you can evaluate upper and lower limits of integration. But yeah, that is definitely a way to find some approximation for an integral of e to the x squared that we certainly couldn't do by any kind of basic antiderivatives or integration by parts or any of those techniques, because integral of e to the x squared is not a simple integral. All right, let's try a couple more of these approximations just to see if these Taylor polynomials are any good for coming up with approximations. So let's estimate the square root of 14. So let's estimate the square root of 14 using a third degree Taylor polynomial. All right, how does this work? Well, the first thing I need is a function. So I'm going to use the function f of x equals the square root of x. The second thing I need is I need a good center. Now, if I center it at 14, then that defeats the whole purpose, because if I knew what the square root of 14 was off the top of my head, then I wouldn't have to use this approximation, right? I would just answer the question. So let's look for the closest value to 14 that's a perfect square, and I come up with x equals 16. So x equals 16, or in this case, a equals 16, will be the center of my series because I know exactly what the square root of 16 is. All right, so if I want a third degree Taylor polynomial, there's f of x. F prime of x will be the derivative of that. So if that's x to the 1/2, then the derivative is 1/2 x to the negative 1/2, which I can write as 1 over 2 square root of x. Okay. F double prime of x will then be the derivative of that. So it'll be positive quarter x to the negative 3/2. So I'll get 1 over 4. X to the 3/2 is the same as x to the 1 and a half. So let's leave it like that. And f triple prime will be 3/8. And then you can see here it'll be negative because I have a negative 3/2. So if I drop that negative 3/2 in front, then I end up with a negative 3/8 and then x squared square root of x, right? Because it'll be 5 halves. What happens when I put a 16 in? So let's center this now at 16. So f of 16 is the square root of 16, which is 4. Okay. F prime of 16 is 1 over 2 times the square root of 16, which is 1/8. The second derivative evaluated at 16 will give me 1 over 4 times 16 times the square root of 16. So that will give me a 1 over 256. And then the third one, and I'm going to check my signs here, right? That's x to the 1/2. 1/2 x to the negative 1/2. Then when I derive that, that one should be negative and the next one should be positive. Okay. So this guy should be negative over here. And now if I derive it again, then this will give me approximately a large number. The 3 on the top, and I'm going to go to the calculator for this one. So I've got an 8 times 16 squared is 256, and then the square root is 4. 8192 is my denominator. All right, so keep those 4 coefficients in mind. 4, 1/8, negative 1 over 256, and 3 over 8192. Those are the coefficients I'm going to need when I set up this polynomial. All right, so third degree polynomial for the square root of x goes like this. Square root of x is approximately f of a, which in this case is just 4, and then it's going to be f prime, so 1/8, times x minus a, well in this case a is 16, so 1/8 x minus 16, then minus 1 over 256, x minus 16 squared over 2 factorial, and then plus 3 x minus 16 to the third. And then on the bottom, we'll go both the 8192 and the 3 factorial. All right, so let's clean this up a little bit. I end up with 4 plus x minus 16 over 8 minus x minus 16 squared over, I'm going to take that 256 and that 2, combine it together to be 512, and then plus, let's see, that 3 on the top will knock out, that thing will then just become a 2, and I'll end up with an x minus 16 to the third over whatever 8192 times 2 is. 16,384. All right, and now we're going to evaluate it for the square root of 14. So the square root of 14 is going to be 4 plus, now, save myself some space. Everywhere I see an x, I'm going to put in a 14. All right, 14, 14. Something kind of interesting happens here. 14 minus 16 is negative 2. Minus, again, 14 minus 16 is negative 2, but this time it's squared. So negative 2 squared is positive 4, so up on the top we'll go a positive 4, 512 on the bottom. And then over here, 14 minus 16 is negative 2. Negative 2 to the third is negative 8. Notice what happens is I'm actually starting at 4, and I'm working my way down. I'm doing 4, and then I'm subtracting a quarter. And then the next term will be me subtracting 4 over 512, which is 0.00781. And then the next term again will be me subtracting something. In this case, it'll be 8 over 16,384. So it's 0.000488. Okay, so you notice we're starting at a higher number and we're working our way down. The other option would have been to start at 9 and work our way up, but 14 is closer to 16 than it is to 9, so we'll do it that way. All right, let's subtract these numbers and see what I get. I'll do it on my end. You can do it on your end. The first two are going to give me a 3.75 minus 0.00781 minus 0.000488. And I get 3.74170. Okay, the big moment. What is the actual value of the square root of 14? So that's my approximation. What is the actual value of the square root of 14? I'll keep as many decimal places, 1, 2, 3, 4, 5. All right. I got 3.74167, so that 5 rounds up to a 6. Well, to 3 decimal places, I actually got the same answer, right? 3.742. So that's not at all a bad approximation considering I only used 3 terms in my series. Had I used more terms, I would have gotten a better approximation. All right, let's do one more thing. Okay. Let's find a series, just one more series example. It's actually not something new. So let's look at y equals the square root of 1 plus x. Let's find the first third degree polynomial. Centered at a equals 0. So if we're going to write it all out in series form, we'd call it a Maclaurin series because it's centered at 0. All right, let's keep the same idea as before. I'm going to make a list of my function and its derivatives on one side, and then the centers on the other. So f of x will be the square root of 1 plus x. F prime of x, if this is really, if we're thinking of it as 1 plus x to the 1/2, the first derivative then would be 1/2 1 plus x to the negative 1/2, which is 1 over 2 square root of 1 plus x. Right? If I derive that again, now I'm going to end up with a negative quarter, 1 plus x to the negative 3/2. I kind of know where this is going, so I'm going to write this as f double prime equals negative 1 over 4 1 plus x to the 3/2, right? Because I just brought it down the bottom. And then the third derivative is going to be positive. Positive what? 3 over 8. And then that 1 plus x will be to the negative 5/2. So 3 over 8, 1 plus x, 5/2. Now, if I put a 0 in for x, this thing actually computes very quickly. The square root of 1 is 1. Over here, f prime of 0, if I put a 0 in here for x, again, I just get the square root of 1. In fact, down the bottom for all of these, if I put a 0 in for x here, if I put a 0 in for x there, if I put a 0 in for x there, I end up with all 1s on the bottom times whatever that number is. So that's why I didn't put it in radical form, because it would have just been messier than necessary. So this one will give me a 1/2. The next one will give me a negative quarter. The next one down here will give me a 3/8. All right, so hang on to those numbers, 1, 1/2, negative quarter, and 3/8, and we're ready to make that polynomial. The square root of 1 plus x is approximately equal to f of 0, which is 1, plus f prime of 0, which is a 1/2, times x minus 0, and then f double prime, which is negative quarter, x minus 0 to the second over 2 factorial, f triple prime, x minus 0 to the third over 3 factorial. And certainly we can simplify this a little bit, right? Square root of 1 plus x, approximately equal to 1 plus x over 2 minus x squared over 8, right? That 4 times 2 will give me 8, plus, 3 factorial, if I cancel a 3 on the top, will just give me a 2, and I'll end up with plus x to the third over 16. So there's my third degree Taylor polynomial. And it alternates plus, minus, plus. You might assume that the next one after that is going to be a minus. So I've taken something, again, that's clearly not a clearly not a polynomial, square root of 1 plus x, and I've turned it into something that is a polynomial. All right, and that ends the material from 11.1 on Taylor polynomials.